Okay, I think we got everything in order. So welcome to a new week. Just to quickly talk about what you guys have this week in terms of assignments, that sort of thing. So we have a lot of content still to get through in physical science, and so what that means is it'll be a lot of teaching and a lot of learning on your part, and probably less assignments than what we've been doing. Which for some of you is a great thing, and for some of you it means it might take one or two more or 1 week longer to get the mark that you were hoping for, or whatever else. But what I posted this week is you have three different things, three different postings. One of them is the week 5 assignment, and that will be only based on 4.5, which is exo and endothermic reactions. That is the one that transfers the most to grade 12 out of the 3 lessons we'll talk about today. So the focus is on that. The second assignment is kind of a fun one for you. It is called the mental health wellness assignment. And all I asked you to do is just post a picture of you taking a mental health break this week. I care deeply about each one of you, wanted to ensure that you are taking time for yourself to rest, relax, read your Bible, pray, play video games, bake, make a video, paint, play music, etc. Um, that'll only be shared with me, but if you want or if you're comfortable sharing it with other people, just leave me a comment, and then I will share that with, I don't know, share it with the class if you're comfortable with that, I suppose. I will also edit the assignment at some point. I'll post a picture of me taking a mental health break as well. I've just been feeling that that has more and more importance right now, and I want to make sure that you guys, I do actually care about you guys, and I want to make sure that you are doing okay. But that being said, we're going to get into something called latent heat today. My goal is to get through just one of these PowerPoints, and then tomorrow I'll release the times. I haven't posted that announcement yet, but tomorrow we will meet up, and I'm going to go through 2 PowerPoints, one of which will be endothermic and exothermic reactions. And then we'll go through the second PowerPoint as well, which will be the heat of formation. So when you're creating products, how much heat is released. But we're going to talk about latent heat today. It shouldn't take a super long period of time. Uh, but basically, we're going to start looking at graphs that look like this. So you can imagine this being the graph of some sort of reactant. And here represented are 3 different states: the solid, the liquid, and the vapor. And you know, if you've ever dealt with water before in your life, which presumably in Canada you have, you've seen ice, you've seen water, and hopefully some of you have made tea at some point in your life or boiled water to make craft dinner, and you've seen steam. So those are the 3 states of water, and they all depend based on the temperature that water is at. And we should know that water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. So there's 2 thresholds, but 3 different states that it can exist in. So latent heat, here's the definition. Adding or removing heat does not always result in a change of temperature. During a change of state, the heat added is called latent heat because there is no actual change in temperature. And the word latent, all that means is just hidden. And so the points that we're talking about today, the only points that we care about are this point here and this point here. So these 2 points are the points where latent heat is being added. The temperature isn't necessarily changing, but it might be that the state of whatever we're dealing with is changing. And so this shows you an example of water. At 0 degrees Celsius, it turns from solid ice. The ice has to melt. It takes time for that actually to happen. The temperature might not be rising during that time period. And we see here, it takes about a minute and a half for all of the ice to turn into water. And then we see here as well that the temperature isn't changing at all. It's dead set at 100 degrees Celsius. But over the course of 4 to 8 minutes, so a span of 4 minutes, it is boiling and then eventually turning all into vapor or steam during that time. So that's what we're going to talk about is these 2 periods, latent, where latent heat is present. The temperature isn't changing, but the state is. So notice in the graph above that while the ice is melting, the temperature stays constant at 0 degrees Celsius. So that's what this is representing here. Our y-axis is the temperatures, our x-axis is the minutes. So the temperature of the system isn't actually changing, it's staying constant. And the same is true at this point here when it's changing to steam or vapor. And this means that even though the temperature isn't changing, latent heat in joules is still being added. So there is still heat being added. There is still heat being added. Or if we were to go in the reverse direction, you could say that heat was being absorbed. It's just hidden in that flat line of the graph because we don't actually see a temperature increase or a temperature decrease, but it is still have technically energy or heat in the form of joules being added in. When a solid is melting, the energy added is building up potential energy of the molecules to break electrical forces holding them together. Again, we said that potential energy is no movement or action is happening. So, in essence, these molecules are sitting still. They're vibrating and moving back and forth, but they are storing up the energy to change into an entirely new state, going from liquid into a vapor. And then the kinetic energy that'll actually happen is the breaking of those bonds. So these electrical forces, this is referring to the bonds between different atoms. Those will break, and that will be the conversion into from potential energy into kinetic energy. So similarly, when liquids are turned into gases, the heat energy increases the energy of the molecules so that they get further apart and become gas molecules. Again, all we're doing is we're adding energy into those bonds, allowing them to separate and separate further and further until they can become gas. It is this buildup of latent heat energy that takes place on the flat spots of the graph. So again, this is just some background contextual information for you. What happens if a change of state? We know of 3 states. There is technically a 4th state, and that state is plasma. Plasma would be things like fire and lightning that have interesting properties that don't fit within the solid, liquid, or gas confines based on the molecular structure that they have. But that's the 4th state. But the 3 main ones that we are concerned with, especially with chemistry, would be solid, liquid, and gas. So if we consider water, water has 3 different states. It can be solid, liquid, gas, otherwise known as ice, water, and steam. So there's 2 different directions that'll happen. These top 2 arrows show the direction of going from ice to water to steam. There are terms that go with that. So fusion, which occurs at the melting point, which we know is 0 degrees Celsius. Fusion is when it goes from ice to water. Vaporization, which we know happens at 100 degrees Celsius in the case of water. That would be taking place at the boiling point, going from water to steam. Condensation, which you've heard of that probably in Science 10 when you were looking at the water cycle. Condensation happens all the time around us. That's when clouds condense into rain, and then the water falls down on us. We can also say that's when water goes from steam back into water. And then the last one that we can talk about is solidification. So from when water goes into ice. So when I was looking at this earlier today, I thought, let's just think about this as 2 different directions or 2 different arrows. There's the top part where you go from ice, fusion, water, vaporization, steam. And then there's the bottom part where you go steam and that condensates into water and then that solidifies into ice. So I thought that was just the easiest way to think about this situation here. So when we get into calculating the latent heat, fusion and solidification, you'll see these 2 here, are going to be the exact same spot. So this would be from ice into or from water. So this is the idea that this can be ice going to water or water going to ice. Both of those use the exact same formula. And so latent heat of fusion, this is the amount of heat required to melt 1 kilogram of substance without changing its temperature. Or if solidification, if we're talking about going water to ice, this is to freeze 1 kilogram of substance without changing its temperature. Again, solid to liquid, liquid to solid. These are just opposites of each other that when we actually want to calculate them out, they combine and they don't combine, but we use the same formula for both. In this solid to liquid, when we're going from ice into water, this causes the sample to absorb heat. In other words, the sample needs to heat up itself, which requires energy so that you can free the molecules from their rigid structure. And then when we're talking about latent heat of solidification, that would be us releasing heat, allowing it to cool down. This process requires that energy be removed from the liquid so that the molecules can settle into a rigid structure. This formula here is the one that is the most important for the latent heat of fusion. It's just called LF, but we use the same formula for both fusion and solidification. So whether you're calculating ice to water or water to ice, you're going to use the same formula. And what this formula is Q represents the amount of energy or the amount of joules that are required for this to happen. So we would call that the heat of transformation. Anytime we have a Q, so even when we're talking about Q is equal to MC delta T, the Q represents the heat or the amount of energy or the amount of joules that are required to have something occur. M in this case is the mass, and LF is the heat of fusion. Heat of fusion. And that will be a value that is given to you. And most of the time, we see that in tables. Sorry, I'm just going to skip ahead like this. So all of the heat of fusions are found under this title here. And then we're going to talk about heat of vaporization after that. The other thing I have to give you is I must give you the melting point and the boiling point as well. So the second one, this again was when we were converting from water into steam or from steam into water. Either of those two, so the condensation would go from steam to water, the vaporization would go from water to steam. So again, it has to deal with 1 kilogram of substance changing its state. So in the case of vaporization, 1 kilogram of substance vaporizing. In the case of 2B condensation, 1 kilogram of a substance changing into the liquid state. And again, it's the exact same information on these two slides here. The left side here, this process requires energy. The right side, when we're going from steam into water, causes energy to be released. So if we're going from gas to liquid to solid, we are releasing energy. If we're going from solid to liquid to gas, we require energy or require heat for that to occur. I'm going to just put a little arrow and say that this could also be heat. So the heat of transformation for these phase changes is called the heat of vaporization, LV. Note it's the same formula for both of these. So again, these two come down and we use the same formula for both. All of the variables are the same except LV here. And LV, what that is the heat of vaporization. So LV is the heat of vaporization. So again, you would get this table, heat of vaporization. All of those values are hidden underneath this little title here. And then we also have the melting and the boiling points. Where that becomes important when we're looking at the graph is if something, let's use this exact example. Let's say that you had your sample going from -20 to 0 degrees Celsius. Let's choose a different color here. So I'm going to choose blue. So during this time period here, where it's not the straight line, you want to use Q is equal to MC delta T. But where it is at the latent heat stage, where it is at this red circle, that's when you want to use the Q is equal to M times the LF or the LC. So that's where you want to use one of those two. And this should be LV, not LC. Vaporization or fusion. Like that. So again, anytime that the graph is increasing, where the temperature is actually changing, we want to use Q is equal to MC delta T. Any point on these graphs where it's a straight line, we want to use the two new formulas that we just learned. The Q is equal to M times LF, or the Q is equal to M times LV. The key thing, the only thing that you really have to know, if we were to write a test in class on this, what I would tell you is the only thing you have to know is what fusion is. So what two states changing between fusion is, and you would say that that would be solid and liquid. And then you'd have to know what two states vaporization changes between. So you would say that that's liquid and gas. And if you knew that fact, then you could solve for these questions a lot easier because it's the exact same formula. Just this value, this LF or this LV, will change depending on what state you're talking about. So first example here. How much heat energy is needed to change 2.0 kilograms of ice at 0 degrees Celsius to water at 0 degrees Celsius? So again, this is important that we actually don't have a temperature change. So I have no need to do Q is equal to MC delta V. However, I am changing from ice to water. And so what I want to talk about then is I want to talk about latent heat of fusion. So Q in this case is unknown. How much heat energy? We don't know. The mass, well, we're told it's 2.0 kilograms of ice at 0 degrees Celsius and water at 0 degrees Celsius. Our heat of fusion in this case, we want to look for water. Is water present on here? I don't think it is it? Oh, yeah, it is right here. So we want to use this value of 3.33 times 10 to the 5. So we want to use LF, which is 3.33 times 10 to the 5. Also, in terms of your grams, you can use kilograms here, and that's shown to you. Ooh, that was really sloppy. But that's shown to you on the actual chart that you can use kilograms here because this unit is joule per kilogram. So plugging this in, we just need to do Q is equal to M times LF. Q is equal to 2.0 kilograms times 3.33 times 10 to the 5. And when you do so, you end up with an answer of 666,000. And the units for this would just be joules. Does anyone have any questions about that first example? Awesome. Next question then. Again, this is a little bit of an easier one. I'll show you a more challenging one in number 3. How much heat energy is needed to change 0.50 kilograms of water at 100 degrees Celsius to steam also at 100 degrees Celsius? Again, because our temperature isn't changing, we have no need to use Q is equal to MC delta T. If you'll remember that formula, the delta T meant a change in temperature. And so if there is no temperature change, then delta T would be 0, and this whole thing would be 0. And so that would be a useless calculation for us to do. How much heat energy is needed to change 0.5 kilograms? So again, I'm looking for Q. I know that my mass is 0.50. Oops, sorry. 0.50 kilograms. And I know that I'm going from steam, from water to steam. So I know that I am looking for a heat of vaporization. I'm looking at water. So that'll be 2.26 times 10 to the 6. So vaporization, 2.26 times 10. I'm struggling with that today. Times 10 to the 6. Plugging all of our values in, we have Q is equal to M times LV. Q is equal to 0.50 kilograms times 2.26 times 10 to the 6. And when you plug that in, you get 1,130,000 joules. And so what probably someone would do is they'd say that this is 1,130 kilojoules. So just multiplying this by a factor of or dividing by a factor of 1,000, and then having your kilojoules values there. So that's the two different types of equations in terms of the LV and the LF. Again, this one was changing from ice to water, so we used the fusion. This one was changing from water to steam, so we used the vaporization. Where that becomes a little bit more tricky is, let's say that we have an example that requires you to calculate the sum of the total amounts of heat involved in the process. Okay, so for this one here, how much heat does a refrigerator need to remove from 1.5 kilograms of water at 20 degrees Celsius to make ice at 0 degrees Celsius? So our hint here is find the heat removed for water at 20 degrees Celsius to water at 0 degrees Celsius, and then find the latent heat for water at 0 degrees Celsius to ice. So what we need to do is we need to figure out all of the value of Q. And so what we need to do is do MC delta T. And so that is finding this value here. That's MC delta T. Finding the heat removed for water at 20 degrees Celsius to 0. And then to change it into ice, we'll have to do M times, well, if we're going from water to ice, it'll be fusion. So we'll have to do M times LF. What we'll need to do is add those two values together. We'll need to add those two values together because they're two separate steps. So plugging these values in here, we know that the mass of this water was 1.5 kilograms. And then in terms of the C delta T, we would want to go to our data table and reference booklet, and we would want to find the specific heat capacity. And what's interesting is this specific heat capacity is in grams. So we will need to represent that first value in grams. Specific heat capacity of water when it's in a liquid state is 4.184. So we want to use for our C value there 4.184. 4.184. The other thing that we need to do is because that is in the units of joules per gram, we need to convert this to 1500 grams times 4.184. And then the temperature change there was from 20, actually, excuse me, it was from 0 degrees Celsius is where we're going to 20 degrees Celsius, like so. So that's the amount of heat that's being removed. And then what we would need to add in is we would need to add in the mass, which was 1.5 kilograms. Um, it can be in different. So this one's in grams. This one's in kilograms. It can be in different units because this 4.814 here was in joules per gram. That's really tough to see, even on my screen. I can only imagine how tough it is to see on yours. Joules per gram. And then this next LF is in joules per kilogram. And so in the end, what we'll be adding up is just joules added to joules. And so it doesn't matter that we have different units there. We can still combine these two values. So 1.5 kilograms. And then we wanted water turning into ice. So we want to use this value here. We want to use 3.33 times 10 to the 5. And when we do so, we end up with an overall heat equal to 373,980 joules as our final solution there. Does anyone have any questions about that example before we move on? Okay, deadly. So last little conversation that we need to have is when calculating the heat of a phase change, you need to take the sum of all the heat values at each step. Notice in the image that there are 5 Q values. Solve for each one of them and then add them all together. So what you would have to do in this case is, let's say you have a 46 gram sample of H2O at a temperature of negative 58 degrees Celsius. How many joules of energy are necessary to heat the ice to 0, melt the ice, heat the water, boil the water, heat the water, and then the total energy in joules? So we need to calculate for every single Q each of those values. So to heat the ice to 0 degrees Celsius, that would require us to go Q is equal to MC delta T. And I'm actually just going to erase that momentarily because I want to just plug it in. So Q is equal to the mass, which was 46 grams. Specific heat capacity of ice is 2.03. And then the change in temperature, we're going from minus 58 degrees Celsius to 0. So 0 minus negative 58. And so that value then would give us 6 times 2.03 times 58 would give us 5,416.04 joules. Huge number. Next step would be to melt the ice. So again, we need to do M times delta H. So this will be Q is equal to the mass, which is going to get converted into kilograms. So this is also equal to 0.046 kilograms. So 0.046. And then we need to go back to that little table and find the heat of fusion for water, which is 3.33, times 10 to the 5. My apologies, I scrolled too far. So this was, get yellow again, 3.33 times 10 to the 5. I'm going to write all of my values for Q over here. So A was 5416.04 joules. B will be 0.046 times 3.33 times 10 to the 5, which is equal to 15,318 joules. Part C. So for part C, we want to use Q is equal to MC delta T again. So for part 3, we're going to put 46 grams times, this is going to be water in the liquid state, so 4.184. 4.184. We are going to 100 degrees Celsius. We came from 0 degrees Celsius. So we have 46 times 4.184 times 100, which is equal to 19,246.4 joules. To boil the water, yes, there's a lot of calculations here. We need to do the mass, which is going to be 0.046 times the H of vaporization, going back to our table, was 2.26 times 10 to the 6. So D will be 103,960 joules. Also notice it takes way more energy to boil water than it does to melt ice. To melt the ice only took 15,000 joules. To boil the water took 103,000 joules. And then the last step is we want to heat the steam from 100 degrees Celsius to 114. So we need to do this. We need to do mass, which was 46 grams, times C, the specific heat capacity. I don't know what that is. 2.01 for steam times 2.01. And then the temperature difference will be 114, which was the final temperature, minus 100 degrees, which is the initial temperature. So we have 46 times 2.01 times 14 is equal to 112.56. Notice how easy it is to heat up a gas once you already have it, only 112.56. And then what we need to do is we need to add all of these numbers together. So 5,416.04 plus 15,318 plus 19,246.4 plus 103,960 plus 112.56. That is equal to 144,053 joules. And that is our final answer. So that's how much energy it took for us to go from negative 58 degrees Celsius all the way up to 114 degrees Celsius. And that is it for this lesson. Anyone have any questions